2017. Sarah, a 55 kg athlete, is competing in high jump where she needs her body over the crossbar successfully without hitting it. Where she lands, a padded mattress cushions her fall. Sorry, I read that out really weirdly at the end there. But anyways, after Sarah has jumped, she lies motionless in position 4 as shown in the diagram. There are 20 springs evenly spaced in the area of the mattress where she lands. The average compression of each spring is 4.5 centimeters. I've converted that to meters, and that is X, which is the extension or compression of a spring. Sarah's mass is 55 kgs, which we already know. Calculate the elastic potential energy stored in a single spring of the mattress. So what are we going to do here? Oh, gave you a wee sneak peek already. So to calculate elastic potential energy, or energy in a spring or elastic band, the equation you should use is, see if you can get it before me, this one, okay? And in order to calculate the elastic potential energy in a single spring, we need the spring constant and the extension. We've been given the extension, cool, or compression. However, we need the spring constant, which we don't have. So we have to go on a little tangent. What is an equation that will help us work out the spring constant? What other equation on your formula sheet has a K in it? Yep, that's right. It is Hooke's law, which is force equals the spring constant times the extension or compression, X. All right, well, let's just rearrange this to find K. We've got X, but wait, we don't have the force on the spring. So we cannot use this just yet to figure out what K is. So let's go on another tangent. We need an equation that will help us work out force. What is an equation that will help us work out force? It's Newton's second law equation, F equals ma, right? So let's start here. I think we've got all the values. We've got acceleration due to gravity, which is 9.8. We've got the mass of Sarah, which is 55. And now we can use these values to work out the force. So 55 times 9.8 gives us 339 newtons spread out on all 20 springs. So how much of force, out of all of this force, how much is a single spring taking upon itself? What do? Well, we'll just have to total force distributed by Sarah and divide it by the 20 springs. So 539 divided by 20 is going to give us 26.95 newtons. So this is the value we're going to use. Let's plug that force value into this equation here. So we have 26.95 equals this unknown spring constant times the compression in meters. So to rearrange to find K, I need to get rid of times 0.045. So I get rid of that by dividing by 0.045 on this side to cancel it out. That means I have to divide by 0.045 on this side. And so K equals 26.95 divided by 0.045. Plugging that into the calculator, this is the value that you should get. This is the spring constant. This is how stiff each spring is. Why the heck do we need this? Well, now we can plug it into this formula here, which gives us enough information to work out the potential, the elastic potential energy in a single spring. So substituting everything in, we've got a half times the spring constant, okay, which we've just worked out here, times the compression squared. All right, and so plugging all of this into your calculator, you should get the energy stored in each spring is 0.606 joules.